Hello, and welcome to Materials Unlocked, the podcast where we take a look at the lesser-known subject of material science and try to unlock its mysteries. My name is Dr. Lewis Owen, and I'm a lecturer at the University of Sheffield. In each episode, with the help of some students, friends and colleagues, we're going to delve into a particular topic and hopefully unlock its potential. And so this is actually our final episode, and we're going to be talking about the big picture, thinking about the sort of broader factors that we might need to consider in material science, things like recycling and sustainability and things like that. Now, as always in these episodes, I'm joined on this voyage of discovery by one of our current students. And this week it is my very great pleasure to be joined by Durga Tilak. Durga, welcome to the podcast.
Thank you, Lewis. It's exciting to be here.
Do you want to just tell us a little bit about yourself? So you're a PhD student. What are you studying at the moment?
So I am researching eddy current losses in permanent magnets for automobiles.
Okay, so this is something I know absolutely nothing about. So these are magnetic materials for cars. So is
Yes,
this
that's right.
particularly thinking about sort of electric vehicles and things like that?
Yes.
So new magnets to make the engines more efficient. Is
Yes.
that right? Or okay.
Yeah, so thereabouts, I would say. So basically, I'm looking at magnets that go inside motors in an electric vehicle. So you have a motor and the battery that act as the parallel, players for, as, the counterparts to the traditional sort of combustion engines that you see in your regular cars. There's been like this great movement that has gone into trying and making them more efficient, because losses that happen by way of heat or eddy current losses, like I just mentioned, contribute significantly to the overall efficiency of the vehicle. And so my research tries to bring down those losses and see whether I can attempt to attack that problem from the materials perspective.
That's fantastic. So are you taking sort of existing materials and then gradually trying to sort of shift them and test the new properties? Is that right? So
Yes. So I'm trying to simulate the behavior and look at systems that are used currently to tackle eddy problems.
Is it mainly modelling then?
At the moment, yes.
Okay. But there's an idea that you'll then
Yes.
do practical things as well to sort of
Yes.
test, right?
Yes.
Yeah.
That's the plan, and I'm quite excited to see how it branches out. But at the moment, I'm just typing away into a computer and hoping that the simulations give me new stuff.
Yeah, that sounds fantastic. Yeah. So just to tell us a bit about your background. So you're a second-year PhD student at the moment, and you're part of the Advanced Metallic CDT, which is this centre of doctoral training in the university, where everyone's looking at something related to metallics. Were you always a material scientist, or did you come from a different subject, a different route?
I wasn't always a material scientist. I like to believe I sort of meandered into it. Which
all the best people did. I did exactly the same thing. So it's
So my first degree was actually a degree in mechanical engineering. And my master's served to be a kind of a bridge between mechanical engineering and materials, because although it was formally a degree in mechanical engineering, I chose to focus on metallurgy for my thesis work.
Right.
And so that it slowly helped me move more from macroscopic parts of mechanical engineering into the slightly finer or smaller microscopic.
So was it really in that master's year that you sort of came across materials, or were there some elements in your undergraduate course that were related to material science? And
I was actually sneakily trying to get closer to materials as I went through my degree.
You always knew materials was your calling.
Yes,
you felt the pull of materials.
Yes. So it was actually something that I did in the second year of my undergrad that was the clincher for me. I knew I wanted to get into materials. I did not know the broad scope that it offered, but I definitely knew that I wanted to step further closer into materials because, I did a paper in phase diagrams and metallurgy and stuff like that. And I was just like, okay, that is definitely piquing my interest.
Yep.
So I knew fairly early on after I had started at engineering school. And I guess the rest of it was just trying to build a journey that ultimately got me into materials.
Yeah.
So stressful but fun.
Oh, it sounds great, and it sounds like you've ended up where you need to be, which is the main thing. So that's brilliant. So today we're talking about the big picture, which is quite a sort of nebulous title, but particularly about sort of sustainability and recycling and those sorts of things. Is this something that you know much about, that you've come across in your degree, or is it something you know very little about?
About as much as someone who has not really traditionally studied the engineering sciences. So it's been things that I have read in the news. Sometimes it has been information that I've had to absorb as a part of like the exam taking that I had to do. So, things like if you're looking at, say, manufacturing, or things like even chemical processes that go into, some of the testing that we do. So it's only been those facets that have in a way coerced me to look at the sustainability angles, meaning what are we doing that might not really work from the environmental angle? Like, are we doing something that's going to harm the environment just in our attempt to achieve, say, a certain objective? That's pretty much what I have really understood from it, but I've never really taken a deep dive into it for the sake of sustainability as a major area of conversation. So
yeah, I think for a lot of people, it's as you say, it's becoming more and more prevalent in news stories and things, and there is this real drive and push to understand how we can make processes greener, improve recycling, improve sustainability, and things like that. And as you say, much the same for me. It's been something that I've sort of come to over the last few years and began to think about more. But I'm pleased to say that we're joined by a specialist who's going to tell us a bit more about this subject. So it's my great pleasure to welcome to the podcast Dr. Richard Thackray, who's a lecturer in the department here in Sheffield. Richard, welcome to the podcast.
Thank you, Lewis. Very nice to be here.
So, Richard, tell us just a little bit about your research and the type of thing that you look at and explore and things.
It's connected with steel in the steel city, Sheffield. Really, it's looking at trying to make those steel processes more efficient. So looking at the whole of the steel making process route from start to finish, trying to look at areas where we can improve the efficiency, trying to look at areas where we might use less resources, for example. Obviously, looking at things like recycling, so looking at waste and byproducts and how we can recycle and reuse those. So it's really taking a snapshot of the whole steel production process and looking at areas where we can make those small or large efficiency gains. Where to start, though? It's such a big. Where do you start?
Well, I think this is, I was going to say one thing that in previous episodes we talked about, in our very first episode, we talked about the materials design cycle in general, going from, having a problem and then developing it. And then in each of the subsequent episodes, we've thought about what one of these stages along the way. But one of the things we talked about in the very first episode is that, for years we've had materials that are suitable for the purpose that we need. And steel is one of those that, steel is everywhere around us. Our entire society is built on steel. And I mean, you may know the statistics. I don't want to put you on the spot about, but I'm sure that the amount of sort of, CO2 or energy that goes into the steel making process worldwide must be phenomenal. And so even slight tweaks or changes that you can make will have huge benefits.
Absolutely, yeah. I'm not sure of the stats, but certainly in terms of energy usage and CO2 emissions, the steel industry and the manufacturing industry in general is a big user of energy and a big emitter of CO2. And so rather than start off with a quite a negative attitude and saying, well, we're never going to get down to zero CO2, you're absolutely right. Making those small incremental improvements, actually, when you add them up at the end of the day, they can make quite a big difference. So yeah, it's looking at those where you can make those, I hate to use the cliche, but low-hanging fruit, where you can make those immediate CO2 reductions, where you can make those immediate reduction in energy, and where we can start to decarbonize on a larger scale.
As I say, steel is so ubiquitous that I suppose we've been doing things a certain way for a very long time. And so we're probably quite stuck in our ways about, and so there's probably some natural human resistance to change and things. So I suppose it can be quite hard if you're then trying to just completely change the process and the infrastructure and things around these things. So those small gains.
Definitely, yeah. And I think that's one of the things we're trying to address. So if you make a change somewhere in the process route, then it always has a knock-on effect further on. So if you make a change at the very top, if you start using different raw materials, for example, then that can have a knock-on effect on things like your material quality. So we always have to bear that in mind, that a change in the process route, it might seem a good idea, but we've got to try and follow that through to see if it is actually a good idea. And one of the things we're trying to do as well is to try and quantify that benefit, if you like. So there's lots and lots of examples where we think we can make efficiency improvements and energy reduction, but we actually have to go through a process of trying to quantify that as well to prove it or disprove it, as the case may be. And you're talking about, it was an interesting comment you made about this sort of resistance to change. It's interesting, if you go back to, let's say, the 1960s, there were a lot of really innovative changes to the steel industry that were planned. But for one reason or another, they never quite got off the ground. But now maybe is the time to revisit some of those. So I think this idea about innovation, people tend to think of the steel industry as a little bit old-fashioned and, as you say, resistant to change. But you go back and you look at some of the innovations that were talked about in the 1960s. They really were state of the art, and maybe they were too ahead of their time. Yeah. So maybe now is the time to come and revisit some of those and see if they can make some changes.
Well, we're sort of dotting around a bit, but one of the things that I was going to mention is among the various hats you wear, I believe you help organise the Hatfield lecture.
I do.
And in 2022, the Hatfield lecture given by Chris MacDonald, he very much was talking about the sort of the history of the steel manufacturing in the UK and, how it might change going forward and the importance of it, not only from a sort of materials and development and sort of green perspective, but also from a social perspective and the role it plays in various parts of society and things, and how those changes sort of come about. So it's interesting to hear you sort of say, maybe now is the time to sort of seize that moment and sort of push forward with the innovation thing.
Well, now's as good a time as any.
Yes, yeah.
And I think what's happened certainly in the UK academic steel academic community is that there's been a lot more, let's say over the past decade or so, a lot more collaborative work. We've always had a really good track record of working with industry, but I think we've had maybe a less of a good track record of working with each other. And I sort of get the feeling that that's changing now.
Right. Yeah.
So there's big groups all working together with a common aim, but also people who are maybe not connected to the steel industry. So environmentalists, mathematicians, data analysts, all coming together to try and see how working collaboratively can improve the situation. So, yeah, it's as good a time as any to make those changes.
Because I feel also with sort of metallurgy in general, and probably more specifically with steel, there's a popular conception that we know all that, like it's all been solved, it's all been done and things. But actually, there's still a huge amount to sort of to do and to investigate and explore. And particularly, as you say, with these drivers of sort of energy reduction and recycling and things, there are potentially new interesting avenues to explore with these things.
Definitely, and I think one of those is alloy composition. So can we take some of these very expensive, ethically dubious elements, if you like, out of our steel and replace them with something that's shall we say, for want of a better word, more environmentally friendly. So there's a lot of fundamental research going on about substitution. Can you take element X out and replace it with element Y? But of course, then what does that do to the mechanical properties? What does it do to the magnetic properties, for example? So every time you change a steel grade, you're almost back to big square one again, where you have to carry out that sort of fundamental research. So yeah, there's still a huge amount, and that's only on the metallurgy side. And yes, of course, another big aspect of it is the process side as well. So how do you make those particular new grades.
Yeah.
So yeah, there'll be plenty of work for
Yes.
the foreseeable, I hope.
So picking up on one thing you've talked about there and something you mentioned earlier is thinking about the raw materials, because in terms of that big picture, one of the difficulties is, where do we get the raw materials? How are they extracted? How do we process them? And then all of the sort of things associated with that. And I know, for example, there's a big drive at the moment to reduce cobalt in various things, and particularly, cobalt is used extensively in battery materials as well as in steel. So some of the things that, the electric vehicles that Durga's talking about and things like that. So could you talk a bit about the sort of our sort of consideration of raw materials and how we take that into account and things?
Yeah, it's as you say, there are many examples of where we'd like to change the composition alloy and substitute, but it's not as easy as that. Sometimes there is this preconception that if you take a nasty element out and replace it with something less nasty, then it's your job done. But of course, you've got to go and work out how much energy and resources have been consumed in taking a new element out, for example. And sometimes the picture is a little bit cloudy. It's not always obvious. There was some really nice work done probably a decade ago where they were looking at reducing the amount of, I think it was niobium in steels. And actually there was some talk that instead of reducing the amount of niobium, if you increase the amount of niobium, you'd actually then decrease your overall energy consumption in the process route.
Right.
So rather than reducing the amount of something that was, expensive, then if you had more in there, you'd actually save energy in the long term. So sometimes it's not quite a black and white picture, and that's why you've got to try and quantify as much as you possibly can, so that you can make these informed decisions rather than guesswork, I guess.
And we've been talking in several of the episodes of the podcast about this sort of balance in materials properties, and very often, you increase one property and another property sort of goes down. And I get the impression that more and more we're considering factors like resources and energy consumption and things almost as a materials property, as something as part of that balance, if you see what I mean, of sort of like, it may improve this physical, the strength or whatever, but then if it comes with this energy penalty or whatever, and then playing that balance between the two.
I think so, and not before time as well.
Yes.
And I think one of those considerations as well, it's something that Durga mentioned earlier, is this idea about designing for recycling. So your work on magnets, one of the considerations might be at the end of life is how you would recycle that. Absolutely. And you might want to then try and think about your composition as to how easy or not that would be recyclable at the end of life. So you can design your material to make it easier to recycle at the end of life. And of course, that's another consideration. You're not just talking about the strength or the magnetic properties, you're talking about the recyclability. But you're also trying to quantify that recyclability as well, rather than just say, yes, it is recyclable or not. You're actually trying to put a value on that.
So you've mentioned a couple of times about like quantification and things, and that seems to be the real sort of, I don't know, the real, or part of the real challenge or difficulty or complexity here, because quantifying these things, which in some cases, I suppose, are easier, things like amount of energy are quite possibly easier to look at, but you've got complex systems with lots of parts and lots of different things feeding into the energy and things like that. So how do we go about quantifying these things?
That's a good with difficulty.
With difficulty.
I think there are certain standards that you can use, but I think it all comes down to choosing the right environmental assessment for the particular scenario.
Right.
So whether that might be a life cycle assessment, whether it be a material flow, whether it be an energy balance, there are different ways in which you can sort of quantify the environmental effect, and it's about choosing the right one. But as you say, a lot of it comes down to how robust your data is. Your output is only generally as good as the data you get. So working very closely with industry to try and obtain the most accurate set of data we can is an absolutely key part of this. And if necessary, you go back to to the very beginning and start generating our own data. But yes, you're absolutely right. It's getting that data is key. And I think trying to split that complex quantification down into more manageable calculations is the way to do it as well. But you're right. It's not easy, but there are right and wrong ways to do it. I think, as there are in everything. Hopefully, we're doing everything the right way.
Yeah. Was it last year? I can't remember. I saw a project that you'd supervised looking at the sort of the flow of a particular element and things. And I think the student who'd been doing it had been in contact with industry and things, but also sometimes you have to get government information and things like that as well. So I would imagine it's quite complex from the sort of, the people who you need to engage with to get and share this information, even before you've got the data, and then working out what to do with the data as well. That's another level of complication and difficulty on top. And things.
I think collecting the data is a project in itself.
Yeah.
And if I remember the project you're talking about, Amy did some fantastic work in some detective work, pretty much, in trying to find out the most up-to-date data set that we possibly could. But that was, that took most of the project, but it laid the groundwork for the work that was going to come after that. So that was the first. If you don't collect that relevant, robust data, then everything from then on is going to be slightly dodgy, I think.
Yeah.
So I just had a question. If I can ask you to please backtrack for a minute. You said that a lot of how one analyzes the data depends on the kind of method that goes into the analysis. So are there set methods that certain people will always fall back to, saying, this is definitely a robust method that's not going to disappoint? Or is it more something that you tailor specifically to the problem at hand every time you have a new project?
Yeah, that's a good question. I think the answer to that is yes and yes. There are ISO standards to follow for life cycle assessment, and we've been fortunate to work very closely with Tata Steel on a lot of this. And they're very heavily involved in sort of setting those standards so that that you're doing things in a proper way. Where you don't have those standards to follow, you almost do have to design your own methodology. And there's some really nice work done at the University of Cambridge. Julian Allwood and Jonathan Cullen down there have done some excellent work over the years, almost developing their own methodology to look at resource and material efficiency. So it's a very different way of doing it, but they've started almost, I guess, from scratch to an extent, and come up with a methodology that then people can follow. So it is really important, where possible, to follow those standard methodologies. If not, then you have to work over a period of years, in this case, to develop and fine-tune your own methodology. And where data doesn't exist, you have to think about how you might generate that data or find that data. But it's the absolute cornerstone of any sort of proper environmental assessment. If you don't get that step right, everything that comes afterwards is going to be a bit suspect, I think.
So in terms then of, you sort of saying if the data isn't there, then you have to sort of create the data. Is some of your work then sort of going to persuade industry and sort of saying, look, going forward, we need to sort of keep track of these things so we can get this sort of analysis done and things?
Absolutely, yeah.
I'm guessing that buy-in from different countries and different institutions and different industries.
Definitely.
Yeah.
And I think where data hasn't been collected before, as you say, trying to arrange for that data collected. Where data has been collected, it's a case of trying to unlock it. And there is so much data generated on the steel plant. From the start to the finish, so much data that maybe previously wasn't thought of as being particularly important, all of a sudden now is, where can we find it? Sometimes it exists on a floppy disk, but that sort of
Windows 95 being booted up.
that leads into this whole idea of data analysis and machine learning and things like that. And again, that idea of data has suddenly become this gold mine which everyone is trying to look at and interpret in different ways. But without it, it's very, very difficult to progress forward properly.
So are these machine learning tools being used increasingly? Because as you say, we've got big data, which is often, associated with machine learning, are they now being progressed to help spot these patterns and flows and things?
I think so. I am certainly not an expert in this field, but I know that there are examples of steel industry in the UK and elsewhere who are using these methodologies to try and improve the efficiency of certain parts of their process.
Yep.
Whether it be in material sourcing, whether it be material separation, whether it be an actual process like iron making or something like that. Whether it's simply a case of making more accurate measurements of composition and temperature, things like that. There are lots of examples of where these methodologies are being applied. And I can see this being a big boom area over the next 3 or 4 years.
Yeah.
Everyone's trying to work out how this technology might benefit their particular process route. And I think also the steel industry can and is learning a lot from other industries too. So there's quite a lot of overlap between the steel industry and the aluminium industry, for example. But also some of the foundation industries, the glass industry, they have big reheat furnaces that use a lot of gas or electricity.
Yeah.
So coming together from the sort of foundation industries is another aspect as well. So it's not just all about data analysis. It's about some of the less glamorous parts, shall we say. The furnaces, what gas you use for your furnace, what refractories you might use. And again, there's a lot of overlap between those foundation industries. And I think both sides can learn from each other in this respect.
So I just had 2 questions actually based on what you spoke about regarding data. So the first was, can you give us examples of exactly what kind of data one may collect when you're looking at the most fundamental kind of steel making method or process? And the second was, are there established data collection techniques that you rely on? Or does it still go back to, the old kind of way where, you're just standing there and taking your readings? And I mean, does it still start at that level, or do we have more sophisticated techniques to get there?
I'll answer the second question first. I think we do have more sophisticated techniques.
Okay.
But in some cases, it is a case of taking manual readings. And again, I guess that's an area of modernization that we can have a whole other podcast.
Yes, yeah.
But it's obviously a really important part. It's not as easy to say you need to get more modern and more sophisticated equipment, because sometimes that's just not feasible. To go back to your first question about examples of data, I think the 2 obvious ones would be temperature and composition. So if you can get a more accurate value of temperature, then maybe you can bring your temperatures down a little bit and reduce your energy bill. If you can get a more accurate value of chemistry and composition, then maybe you can stop your oxygen blow a little bit earlier in the steelmaking process, and you can save oxygen and you can improve your efficiency that way. So there are lots and lots of examples of where just an accurate value of temperature and composition could help you to improve your efficiency. And that's, even before you start thinking about some of the other more slightly sophisticated data collection. But they're 2 examples that they immediately spring to mind. And I think, again, where the industry has been able to use more sophisticated data collection techniques, I think they can see the benefit of that. It doesn't take long to demonstrate that you can make efficiency gains over a period of 3 or 4 months if you are able to adopt this technology. Yeah, and I think that the more and more examples that you can show of that, the more likely it is that the industry will start to adopt those. But it's not as straightforward. Obviously there's a cost implication and a resource implication here, as well as a skills implication too, because you can have the best data collection technique known to man, but if you don't have that ability to analyze that data, the skills and the training and the knowledge to analyze that data, then you're sort of you're groping around in the dark.
Yeah, just to go back earlier when we were talking about the different techniques for analysis and things, you mentioned a couple of things. You mentioned life cycle assessment and also energy balance. I wondered if you could just explain a bit more about what those are. What exactly is a life cycle assessment? What takes place during that process and things?
I guess it's really an inventory. It's a data collection process. So you look at what goes into a process, you look at what comes out, and then there are various packages that allow you then to put a sort of value on there, various categories of CO2 or eutrophication, all sorts of different sort of categories that you can start to put a value to. But the key to any life cycle analysis, I think, is carrying out that inventory, that before and after. And again, there are fairly good guidelines and templates for how you do that. But obviously, it changes depending on what your particular process is. So that's almost the same as an energy balance or a material or resource efficiency balance. It's a comparison of before and after. So what goes in terms of water and electricity and energy and raw materials and how much of those raw materials as a comparison of what comes out. So it sounds simple, but of course it isn't.
Well, I was going to say, it's the complexity of the system that's involved, because you're talking about data and things. One thing that people are increasingly talking about and being aware with big data is obviously big data has to be stored somewhere, and there is then an energy associated with that. So, I suppose with all of these things, you've got incredibly complex systems, and the question is sort of, it's not a question you can answer, but I suppose the difficulty is knowing where to stop counting. With the sort of like, what energy it sort of falls within my sphere of sort of this is related to this system. Because if, as well as, all those processes of cooling and heating and things, you're also collecting data and then storing that data, do you consider the energy associated with storing that data as part of the process? And so I'd imagine it's an unenviable task.
And I think, that there are some real experts working on this in and not just in metals manufacture, but in all sorts of different examples. But setting your boundaries is a key part of that, and breaking that down into slightly more manageable rather than looking at everything holistically. But yeah, you're right. It is complex, but if done properly, it does shine a light onto, it really does open up this window of understanding more about what that environmental effect might be. So really important part, but as you say, complex and ever-changing, shall we say, as well.
Yeah. One thing I also wanted to pick up that you said is, and this is probably going to be a completely dense question on my part, but you were talking about the energy, the process, and obviously you've got furnaces and things which you're heating to huge temperatures. Often with these things, a furnace is never 100% efficient. You get heat loss and things. Are there efforts to sort of recapture that heat and things that's being lost and move it into other things? Is that something that's already being done, or is that something that we're trying to do with the sort of process?
It's something that is already being done, but there's still a lot of work to go on that, I think. So we're involved in a big manufacturing hub called Sustain. I think I mentioned Sustain. And we're partners with the steel industry and also the University of Warwick and Swansea. And we're looking at the whole steel process from start to finish. So the raw materials from the iron making side all the way through to your finished product and beyond in some cases. And one of the tasks is to look at that sort of waste heat recovery. But again, it's something that sounds reasonably straightforward on paper, but these are always the most complex when you actually come down to it. How do you capture it? Where do you store it?
Yeah.
What's the best place to reuse it? There's some great examples of waste gases produced in the steel process that are used elsewhere. They're used for reheating bits of metal in other parts of the steel plant. They might be reused in completely different applications, so agricultural application. So as long as you can transfer and pipe that, then you have a potential reuse of those gases. But again, the more you drill down into it, the more you realize that, again, it's a very, very complex thing. But it is something that is being done, and I suspect it's been something that will, again, blossom over the next few years or so. There's still a lot of interest in how you use that let's not call them waste gases, let's call them byproducts.
Yes. Yeah.
How you can use them elsewhere, whether it be in the steel industry or whether it be in a different application. This great idea of industrial symbiosis where one industry's byproducts are another industry's inputs. It's a great model to look at.
And you talked earlier also about recycling, and I think this is a big one that a lot of people are, a lot of people will be familiar with recycling of paper and plastic and things like that, but they might think of, tin cans in the kitchen or whatever being recycled, but they won't necessarily think about recycling on that sort of industrial scale. So what sort of challenges does recycling have associated with it? And, what sort of things do we need to take into account when we're thinking about recycling steels or whatever metal it is on that sort of big industrial scale?
Yeah, it's an interesting point because, when I was younger, many, many years ago, aluminium was the metal to be recycled. Mm-hmm. You saw aluminium recycling everywhere. But steel is the most recycled metal in the world.
Yeah.
And there's an old cliche that you can infinitely recycle steel. And steel that might once have been part of a bridge is now part of Wembley Stadium and so on and so on. But whether you can infinitely recycle steel or not is debatable, because the more you recycle steel, the more you build up concentration of elements like copper and nickel that you can't easily remove, and they start to affect negatively the properties of your steel. So there is that problem with constant recycling. You start to build up these what we call residual elements, and they tend to be harmful to the properties of steel. So that's the first challenge. It's one of the first challenges. I think the other is the quality as well. How you actually transport your scrap steel, how you segregate it, how you measure the composition, how you make sure that you have the right chemistry. These are really, really difficult challenges. And if you go and visit a scrapyard for a steel company, you immediately see the size of these challenges. So it is a very recyclable metal. We want to try and recycle more of it. There are environmental benefits of using recycled steel. We want to try and keep more of that recycled steel in the UK as well. But that probably is something that isn't going to be solved by university research. It's a policy that needs to change.
Yeah.
So you can see the advantages of recycling, and maybe we will move to a completely recycled steel process in 30, 40 years' time. Who knows? But there are also challenges that need to be overcome to do with the quality, to do with how you recycle it, to do with the energy required to recycle it as well. And again, these are really important bits that are being studied at the moment.
Because in previous episodes, one of the things we talked about is qualification of materials, and that materials testing and making sure something is safe and fit for purpose. And I suppose picking up on what you've said here, that's then part of the challenge is when you've got these concentrations of additional elements that you can't easily extract and things, it might mean that it moves below a certain qualification line, which means it's no longer suitable for
absolutely. So I think there are two solutions to that, Lewis. I think one of them is to try and make the input scrap material that you are recycling cleaner, so that you don't have the problem with these concentration buildups. The other is to change the standards. And say that, do we really need those standards now? Those standards might have been written 30, 40 years ago. Are those standards still fit for purpose? Or do we need to change them based upon, the experience of the last 3 or 4 decades? Either way, either of those solutions is non-trivial. But yeah, it's a good question about standards and qualification. There's some really nice work that we're doing with the University of Swansea, potentially looking at a sort of digital materials passport. I can't tell you too much about it, mainly because I don't know so much about it. Not that it's confidential. But this idea of capturing the provenance and the history and the properties and the recyclability of a piece of metal in a sort of digital passport, that's a really nice goal to think about. Again, how you do that is a different matter, but that end point of being able to do that is really quite interesting.
Yeah, I was going to say the Materials 4.0, which is this idea of digital within materials and how we go about building that sort of data and digital side into the process. And as you say, these digital passports, where we track a material through its potentially entire life and things. I understand from speaking to various people, there are always complexities with things, again, about, how much information do you include on that?
Yeah.
It's very difficult, again, to know where to draw the boundary and keep track of that throughout its life. But it would certainly potentially, as you say, I suppose, allow us to, have a better idea of the sort of things that might be in the material and how that might affect what's going into recycled products.
Yeah.
So I also had another question regarding, the idea of recycling. So, once we become aware of the fact that a bit of scrap metal can be recycled, right? So I was just wondering, does that awareness also act as an input to the next time when you're designing the material in the first place? Which is to say, like, if you're aware of the difficulties that go into possibly reusing a piece of scrap, is there any way that we can fundamentally design that bit that has at this point becomes scrap? Can we design it in a way that when it's fresh off or fresh out of the industry, it's going to be living, say, the duration that it's supposed to live as the original product, but it's still going to be in a state where recycling it is going to be easier, say, at the end of its original lifetime?
Yeah, I think that comes back to that idea about designing for recyclability that I talked about earlier. And I think the first time I came across that was the aluminium industry, where just tweaking the composition of your drinks can actually have a big effect on the recyclability and therefore the energy efficiency of the recyclability of your piece of metal. And I think that is a really nice goal to aim for steel as well. It's easy. All these things are easier said than done. But if we can design and tweak and fine tune the composition so that at the end of life, however long that might be, you can safely and easily and efficiently recycle it into something else or recycle it again for the same application. Again, that surely is a really good goal to aim for. But then you come back to this idea of fundamental understanding of what happens when you melt a piece of metal. What happens to those elements? Because those elements don't all behave in the same way. It'd be great if they did. They don't.
Yeah.
So alongside some process work, there has to be this fundamental research that goes on to understand more about what happens to the different elements. But then you've got a really nice mix of process and fundamental metallurgy. You've got the sort of bones of a really nice project, haven't you?
And I suppose one of the things we haven't really talked about, but we've been thinking about sort of basically taking the existing process and making it more efficient. But I suppose a slightly different way of thinking about it is, if you could make a steel or whatever material it is, but that has an extended life, obviously the energy output sort of per unit time, it then becomes more efficient to make that sort of steel. So I suppose that's the sort of other way of looking at it and how we can go about designing new materials that might have longer life. And so even if they might then be require a slightly higher energy process to make, or have raw materials that have a slightly higher energy process, that might be a price to pay if you end up with a better material. Is that
absolutely? Yeah, and I think that's the sort of thing that can sort of get lost in the whole idea of sustainability. That there are many examples of where you can design an object, as you say, that has maybe a better corrosion resistance, better high temperature corrosion resistance, that meets the definition of sustainable. This idea of improving the lifetime, as you say. You'd still probably need to do the calculations.
Yes, yeah.
Quite often they do come out that, if you improve the lifetime by 5-10 years or so, then you've made a more sustainable, in inverted commas, material. Sometimes that gets forgotten about. So there's some really nice work going on to look at stainless steel, for example, where if you can improve the corrosion resistance, you extend the lifetime, and innovations in stainless steel production means that your embodied energy can come down as well. So you've got to win. And sometimes it is as simple as that, shall we say. I'm not saying that is necessarily simple, but absolutely. And that doesn't apply just to steels as well. It applies to very complex, the superalloys, for example. But yes, you're absolutely right. It can be as simple as that.
So thinking then in sort of in more specific detail about the steels industry and your work, can you tell us a bit about, what's going on at the moment and some of the things people are doing with regards to, in increasing recyclability or sustainability and things within the community?
I'll give you one example, I think, and that's at the very, very start of the steelmaking process, or one of the steelmaking processes, is actually to make iron. So generally that will be done in a blast furnace. And if you look at the calculations, that's where the most energy is used, where most of the CO2 is emitted. So it's an obvious place to look for efficiency gains. And the blast furnace has been used in similar forms for thousands of years. So you dig things out of the ground, you blow gases at it, you turn iron ore, and you get liquid iron. In IJmuiden in the Netherlands, Tata have been looking at a different way to make iron. It's called Hysana. You basically have the same ingredients to an extent, but they haven't been prepared as much, so it's much simpler preparation route. And you get liquid iron out at the end. So that is undergoing, has been for 5 or 10 years or so, a series of full-scale trials that have been ramped up. But it is seen to be a much lower energy process, if you like, a much more efficient process than the blast furnace process. So that's one example, I think, where the industry is really looking at trying to make these revolutionary changes almost. And I suppose that the other end of that is looking at electrolysis as well. So electrolytic production of iron. So much the same way as you can make titanium and aluminium from electrolytic processes, you can do the same with iron.
Could you just explain very briefly what an electrolysis process is for
I guess
the listeners?
It's taking your raw materials and passing a current through them that separates the oxygen from the ore.
Yep.
So you're taking iron oxide, if you like, and you're producing iron. And you can do that with tantalum and titanium, and it's the only way in which you can make aluminium. And again, there is a lot of interest in doing this for iron because of the potential advantages. There's no need for blast furnaces. There's no need for coking ovens. There's no need for all these really energy-intensive parts of the process.
And particularly if we can move over to a green energy source that provides mass electricity.
So it's in its infancy at the moment, but you can see the benefits of this. It won't replace conventional steelmaking, but it might make a difference. And I think if we go back 25 years when this was applied to the production of titanium, you can see how that's come on in leaps and bounds. So there's both ends of this steelmaking route. There are lots of innovations going on, but again, coming back to sustain, we're looking at everything from alternative casting processes, new materials for iron making, better data capture and analysis. We've already talked about late definition product changes, where you make very, very late changes to the production route to change your mechanical properties. There's so much going on.
And as you say, you've got to have that holistic entire view of the entire process.
Yes.
And
I think that's really important. I think that knock-on effect that might be negative. You have got to understand the implications of how something at the very start of the process might affect something at the very end. And having that that holistic research philosophy, I think, is really important.
Richard, that's fantastic. Just before we finish, is there anything else that you wanted to tell us about, any of the topics that we've covered today, any of your research, and anything in particular that you enjoy about material science that you find particularly interesting or anything?
I think one thing I will say is, because it's interesting you asked Durga about how she got into material science. So I did a material science undergraduate and postgraduate.
I think you're one of the few people who we've spoken to who's been a material scientist all the way through.
It's a rare breed. But I did my PhD on aluminium. So I started off as an aluminium metallurgist. And then I got the opportunity to work in the steel research theme and never really looked back. And I think once you get in, certainly, well, my experience anyway, getting that first taste of steel gave me a real drive to try and eventually research into some of these potential efficiency gains. There was so much to do. There was you could see all the way along, right from the very beginning, that there were these opportunities there. And I was really lucky to work with two really good mentors, one academic mentor and one industrial mentor, at the right time as well.
Yeah,
and I think that was a really important part of my career. Not that being given that opportunity to work with these people, to realize those opportunities, just to try and put into action some of those opportunities that I'd seen, I think was really important. So it just goes to show, I think, that you can have that sort of late-ish career change, if you like. Don't worry about specializing too much.
I'm so glad you said that.
There is always that opportunity. I think the skills I learned from a degree and doing an aluminium PhD, they were quite transferable to working on a different metal. Yes, there are differences, but don't worry too much about specializing, because I don't think you're specializing too much, if that makes sense. There's always that opportunity, and the skills you learn that you might not immediately see are applicable and transferable. They actually are, I think, at the end of the day.
Yeah,
that's great. Thank you, Richard. Durga, do you have any final questions for Richard, or anything that you'd like to tell us about?
I think in all seriousness, we should definitely do another episode, because I don't think one is enough, because there's just so many interesting things that you said, Richard. And then, I would have loved to just keep going with the questions, because everything that he said has had some kind of a ripple effect in my head, where I'm thinking, okay, so how do I understand this in the context of, say, something I've read in the past, or something that I might be thinking about implementing in my project. But I think that's also the beauty of materials, right? It's what he said. You'll find that tiny concepts tend to find application or have applicability in a completely different corner of the materials world. And just knowing how to approach a materials problem teaches you a lot about problem solving in general, right? And I think I love that, because I am a bit of a poor decision-making person, in the sense that it's very difficult for me to choose from things. And I think that's what I really love about materials. It lets you, take a dive into the broadest kind of areas, but you'll still find that little thing that you eventually gravitate towards, that you feel like focusing more on. So it does the decision making for you, I think, on some levels. So yeah, I think that's what really excites me a lot.
I think there's, again, going back to that old cliche about steel, everything is either made from steel or using steel. But everything comes down to material at the end of the day, doesn't it?
Yes. Yeah.
And I think that's why we're here talking in this podcast, because we've all been sort of bitten by the bug, haven't we? In different ways. In different ways, and I think that's just those examples that we talked about today, but also in the rest of the series as well. Why not? Let's do another one.
Yeah. Well, I question for you. When are we doing the next set of episodes?
Yes. So this is the last episode of this series. And in this series, we've looked at the whole materials design cycle and going through and looking at some of these things in more details. But hopefully, listeners, this won't be the last you'll hear of us. And hopefully we'll be back again talking about other things in materials and other areas of materials as well. This series, we focus very much on metallurgy as a case example. But that is just one of many, many different materials that we could have talked about and done whole series on. So hopefully we will be back in future to talk about these things. But I think for now, that's a fantastic place to leave it. So I'm going to thank Richard for his time. And thank you, Durga, for joining us and asking questions as well.
Pleasure.
And as always, thank you, listeners, for tuning in. And as I say, hopefully we'll be back soon. Thanks very much. Thanks very much for listening. If you want to join the conversation, you can find us on Instagram @MaterialsUnlocked. If you want to find out more about the topics that we've covered and the work that we do, a link can be found to our website in the show notes. Our thanks to the Advanced Metallic Systems CDT, the Henry Royce Institute, and the Department of Material Science at the University of Sheffield. See you next time.